he will give a poster presentation about quantifying deterministic chaos of flows transported in fully baffled sealed vessels by the finite-time Lyapunov exponents. Okay, thank you. And you can start now.
Okay. Hello, everyone. My name is Kunli, and the topic is Quantifying Deterministic course of flow transport in fully baffled stereo vessel by Finite-time Lyapunov exponent. So the main objective is to know how the flow transport in a stereo vessel. I will introduce my research in this following 5 aspects. As we all know, mechanically agitated vessels are widely used for chemical, pharmacy, food, and petroleum industries. It's a very popular device for industrial. But now the problem is because of the lack of enough and detailed understanding of multi-phase flow, and we have a limited predictive capacity of flow behavior. So the industrial don't know what happened inside. So they usually use the global black box method for operation, design, optimization of industrial equipment or processes. Sometimes they only change the input and like the parameters or the concentration or other things, the input of the process, and they will see what happened of the process output. If the output is good, they think the input is the optimal one, but actually they don't know what happened inside. Because the complex multi-phase flow is a very complex flow. Flow transport property depends on many factors, like phase properties, system geometries, flow regimes, process parameters. It will lead to complex flow transport course. Like this picture, the only difference of the impeller type, it will lead to a quite different flow transport in the stereo vessel. The good news is recently Lagrangian coherent structures have been provided with its efficiency to evaluate the flow structure and reveal the complex flow transport behavior in many applications. So my objective is to develop a data exploration platform to identify specific Lagrangian coherent structures, to understand and predict the behavior of complex flow transport in stereo vessel. So this is the workflow of Lagrangian flow feature exploration. First, we use a numerical simulation, or we use measurement to get the continuous flow velocity field in the stereo vessel. And we input the velocity field into the data exploration platform, what we built. In the platform, we will calculate the FTLE, and it will give us the LCS, the Lagrangian coherent structures, and it will tell us to how the flow transport in the tank. So here we use a simple case, single liquid turbulence flow, to demonstrate the feasibility of the built data exploration platform. Okay, the first we need to know what is LCS. As already demonstrated in these two papers, LCS is defined by FTLE reaches, which include forward FTLE reaches and backward FTLE reaches. The forward FTLE reaches corresponding to repelling LCS, and the backward FTLE reaches corresponding to the attracting LCS. Both repelling and attracting LCS are flow transport boundaries. That means the flow cannot go through of the boundaries. But the repelling LCS and attracting LCS have a little difference. Here we go to an example. If you look at the figure A and B, this is the velocity field at two different times. In this domain, we can see here two vortexes, here the left side and the right side, but the time is changing. The velocity field is changing. So we cannot, if we want to study how the flow transport in this domain, it's hard to get the answer from the velocity field. So people usually use ink as a tracer. For example, we put ink point, the black point, in the domain, and after a period of time, we see how the ink shape it looks like. So at the after a period of time, at time 1, and the ink shape it looks like the figure B. So we can see from the figure 1 to figure B, the shape changes with the effect of the flow. But why it changed? We can see one ink point, it become two parts. The one part is the left part, and the second one is the right one. They are not connected. They are two separate parts. Another thing is the shape of the left one and the right one is different. So, but why it looks like it, or why the flow transport makes the ink looks like it? So here we use the repelling LCS and attracting LCS to explain it. If you look at the figure C, here is FTLE, the forward FTLE map, and the white one, the white line is the forward FTLE ridge. It corresponding to the repelling LCS. The meaning of repelling LCS, it can explain how flow behavior in the future. That means at current time, T0, we inject ink point, how the ink will go in the future. So we can say the white line separates the ink point into two parts, the red part and the blue part. Because we say the both repelling and attracting LCS are transport barriers, transport boundary. So the LCS separate the two parts will go to different regions. So at T1, we say the red line and the blue line is the shape of the point of the two-part point. But why the at the time t1, the shape looks like this. So we go to attracting LCS. We say figure D. We call this attracting LCS as hindcast. And that means it can explain why the flow behavior like its history behavior. That means the thing happens, we can know the reasons. And in figure D, this is a backward FTLE, and the black line is the backward FTLE ridge. And we know the attracting LCS is also a boundary. So the red line and the blue line at the different side of the black line, because the black line is a boundary. So because attracting LCS has the attracting nature of a neighboring flow element. So the flow near the flow element near the attracting LCS, it will with a period of time, the flow finally will get the shape similar like the attracting LCS. So that's the reason why finally the ink will looks like in this shape. So this is LCS. And how to calculate the FTLE? I don't talk too much at here. You can refer to the two paper. And the important thing is when you calculate the FTLE, you need some parameters: calculation domain, initial time, integration time, and the most important is continuous velocity field. This velocity you can get from simulation or measurement. Here we go to our simple case. This simple case is a single liquid turbulence flow, and in a fully baffled stereo vessel. The vessel is a cylinder tank, and 4 baffles on the wall. And the impeller is pitched blade turbulence, and it will be pumping downwards. And the impeller clearance is 0.33 of the height. Rotation speed is this number. It's corresponding to a turbulence flow. Because in industrial we have a conventional concept, we think the flow in the tank is axisymmetric, but actually in flow transport it's quite different. So we select different azimuthally plane, like 5 degree to 85 degree. We select many slides plane of at different azimuthally position. And we use the integration time 1 second. And the velocity field is from the numerical simulation. And here is a process how to calculate. From the CFD numerical simulation, we use the O'Leary method and steady state to get the result, and we output the velocity field at each azimuthally plane, and we use a mesh to calculate the velocity field at each position, and then we get the velocity field. We can see from 5 degrees to the 85 degrees, the mean feature of the velocity field is similar, but there are some small difference. If we calculate use our data exploration platform, and we will get the forward FTLE field and the backward FTLE field. And we use a ridge extraction algorithm. We will get the repelling LCS and attracting LCS. So if you look at the velocity field, the mean feature is similar. The only small difference at a different position. But if you see the repelling LCS and attracting LCS at each plane, it's quite different. So for the flow transport accept, we say the conventional concept of axial symmetric is not true. For example, at the 5 degree, the 5 degree is it's called just after baffle. If we go back, we can see here is a flow direction, and here is a baffle. Just after baffle, 5 degree. This is a plane. We call it a 5 degree. So you can see, because we know the attracting LCS, it has nature of attracting. So you can see almost at this region, almost all flow elements will go to the tank boundary and go and flow up. But if you see just before the baffle, that means 5 degree before the baffle. So the flow element here will go down. So it's quite different. Even for the velocity field is similar. And another finding is at all position we found here just below the impeller. Here is a boundary. This boundary partitions the flow into 2 different regions. We call here is up flow, up vortex, and here is a bottom vortex. And you also can see at each position the shape and the flow transport at the up and bottom is quite different. So the simple case has demonstrated the feasibility of our built data exploration platform, and it revealed the flow transport feature in fully baffled stereo vessel. And we use the simulation data to verify it. Here is the three conclusions I just mentioned, so I do not speak anymore. Thank you for your attention. And do you have some question?
Thank you. Thank you for your excellent presentation. And
Oh, Kunli, yeah. Can you hear me?
Yeah.
Yeah. Hello. Thank you for presentation. I have a question. Can you move your slide to the deploying LCS and attracting LCS? Yeah.
Here?
Yeah. Repelling LCS. Can you brief me introduce what is the principle for this method can predict the future of the turbulent flow? Thank you. And also, I have the second question. It is that because we know that in the turbulence flow, there are different scale. For example, like the range scale, and
Yeah.
if we go more deeper, it is LNS, the large eddy simulation.
Yes.
And now it is the most cutting edge. It is the DNS, direct numerical simulation. I wonder which scale you are using to simulate the chaos in your flow reactor. Yes, thank you.
Okay. The first question is what's the principle of repelling or attracting LCS? So if you just if you just think the LCS is a name, and we also call it FTLE ridge, because it's the same meaning, just like the white line in the figure C, and it has ability to explain how flow behavior in the future. Why it can do like this? Because it take FTLE calculation is a forward calculation. It takes the velocity field from time 0 to time 1. That means I use future data to calculation and to predict the flow behavior in the future. So this is the principle. For the backward FTLE or the attracting LCS, that means at time 1, I use the velocity field from time 1 go back to time 0. So that means I use a history data to understand why the flow behavior like this, because the flow we already know how the flow behavior, but why we want to go back to find the reasons. So it's a different function. Then the repelling LCS use future data to predict the future behavior, and the attracting LCS use history data to explain why, to explain the reason. So this is the first question. And the second one, I think you might interest here. Actually, for turbulence flow, you are right. There will be a different scale of eddies, but here we just use a steady state to simulate. But if we use another how to call it instantaneous simulation, it will quite different, because here we only want to know our objective is to know at different azimuthal position, that means at different degree, how the flow looks like. If you use another simulation, the results is quite different. For the CFD simulation, I just use the results from our group. If you have more interest, you can go to this thesis. Any more?
Okay, thank you. Thank you for your explanation. Thanks for the questions from Renjo. Any more questions? I think We don't have further questions from the participants.
Yeah.
Yeah. Thank you. Thank you for your answer from Rindong.
Thank you.
Thank you. Thank you for your excellent presentation. Thank you.